So I'm Henry Segerman. This is a JMA talk. So this is a paper that I wrote with Royce Nelson on visualizing hyperbolic honeycombs. So these have three-dimensional cells in them, but they're not at all biological. And like the previous two talks, they're very, very rigid and mathematical and not squishy at all. So let's get started. So first of all, let's start in 2 dimensions, because we're going to be going very soon to 3 dimensions with some very nice tilings. So let's start with this one here, the tiling of the plane by squares. And what I'm really introducing here is these things called Schlafly symbols. So this down here, 4, 4, that's the Schlafly symbol for this tiling. And the way that you read this, so there's 2 numbers. The first number tells you how many sides do the tiles that you're using have. So squares have 4 sides. And then the second number tells you how many of those meet at each vertex. So if you have squares and 4 meet at each vertex, you get this tiling. If instead you say, well, I still want to use squares, but I'm going to have 5 meeting at each vertex, then it's no longer a tiling of the Euclidean plane, it's a tiling of the hyperbolic plane. So, you know, this is the Poincaré disk model. If you've seen the Escher pictures, it's the same sort of thing. You have too much stuff there if you're putting 5 squares around each vertex, so you have to go to a different geometry. And then back down this way, what if I want squares, but I want 3 around each vertex? What's that going to make? That's going to make a cube. Well, so instead of being on the plane or the hyperbolic plane, I want to think of this as being on the sphere. So if you imagine a cube and then you sort of inflate it to make a beach ball, then you're going to get a cube-like tiling by squares of the sphere. And what I've done here is I've projected it out onto the plane so that we can see, you know, the commonalities between these different ones. Now down here we have the dual tilings. So in case you haven't heard of what a dual of a tiling is, what you do, let's go over here maybe. So you have a square over here and you put a vertex in the middle of that square, which is going to be that vertex there. And there's a vertex in the middle of all of the different squares. So there's these 3, I guess 4 vertices around here correspond to the 4 squares here. And then you connect up with edges when you connect the dual up with edges when the squares share an edge here. There's an edge between the 2 vertices there. And the one thing to notice, maybe you can sort of wonder to yourself about why this is true, the duals of these tilings, you reverse the Schlafly symbol. So, well, the dual of the square grid, Euclidean grid, is the same tiling, but it's just sort of shifted. And here, you know, you've got a vertex here that has 5 squares around it. Well, that's going to turn into a pentagon. So while we're here, whoops, where am I? So this is new since the paper was written. Royce set up this tiling bot on Twitter, and every day it tweets a new picture of some tiling. And these all have the Schlafly symbols in here. So this is, well, some fancy tiling dual to a truncated 411. So presumably there are 4s and 11s in here. So yeah, tiling bot on Twitter. If you're on Twitter, go follow it. So what about, right. And so there were different geometries that we saw in these cases here, Euclidean, spherical, and hyperbolic, and the same thing is going to happen more generally. And you can sort of draw a map of where the different tilings are, where the different geometries are. So here's 4, 4, and that's on this line of Euclidean tilings between the spherical and the hyperbolic. So here's another one. So this is 6, 3. So what's that tiling? It's a Euclidean tiling. Hexagons, 3 around each vertex. This one up here is triangles, 6 around each vertex. Down here, these are the Platonic solids, tetrahedron, cube, octahedron, or possibly the other way around. And then all of these things are hyperbolic tilings. So you get this very nice. So these Schlafly symbols are wonderful. They don't describe a huge, well, they do describe a huge variety of tilings, but in a sense they're very restricted. They have to be very regular tilings. But it's a very nice way to organize them. And this curve here is given, it turns out, by this equation. Okay, now on to 3 dimensions. So in 3 dimensions, the symbol gets an extra number on the end. So how are we supposed to read this? The first 2 numbers tell you the cells that you're going to make your tiling out of. So 4, 3, I've got squares, I've got 3 around each vertex, so that's a cube. And then I'm going to take those cubes and make a 3-dimensional tiling. And this one tells you how many of those cubes go around each edge. So 4, 3, 4, I've got cubes with 4 around each edge. That gives you the Minecraft tiling of 3-dimensional space. If instead you take cubes and put 3 around each edge, then you don't get a Euclidean tiling. You don't get a tiling of 3D Euclidean space. You get a tiling of 3-dimensional spherical space. And this is, I guess, another way to see this is this is a tiling of the hypercube. Well, this is the hypercube tiling of the sphere. So I'll just hand around this 3D print so people can look at that and verify there are indeed 3 around each edge. What if you want 5 cubes around each edge? Now you have to go to 3-dimensional hyperbolic space, and it gets kind of hard to see what's going on. So I'm going to sort of go through this picture a couple more times with different ways of drawing it, but there are all these cubes sitting inside of a 3-dimensional version of the Poincare disk model, the Poincare ball model, and there are 5 cubes around each edge. So let's get another picture of this. So we're going to do layers of these cubes so you can see how they sort of build up outwards. So here's a cube in the middle, and you can see that it's a little bit spiky because things get spikier when you're in hyperbolic space. And then we put 1 layer of cubes on the outside, 2 layers. So let's just look at this edge here. There's a cube there. I've added 2 more, so now there's 3 cubes around this edge. And then I've added 2 more, another layer. Now all 5 cubes around this edge. You can't see it anymore. Still, it's kind of hard to see what's going on. Actually, let me switch over this. This is another thing that wasn't in the paper last time. This is some new work with a student of mine, Michael Woodard, doing a sort of simulation of hyperbolic space where you can see, this is sort of, if you're inside of that tiling, then hopefully you can see around this edge. Maybe I'll just reduce the edge thickness a little bit. There are 5 cubes around each edge. Maybe you can see that. OK. So you can do duals as well, of course, in 3-dimensional tilings. And again, the Schleifli symbol reverses. So here I've got the central cube of the hypercube tiling. So that's cubes with 3 around each edge. And so how do you make the dual? Well, this time, instead of putting a vertex at the center of each square, we're going to put a vertex at the center of each cube. And then you're going to connect those vertices together by an edge if there's a face of the tiling by cubes which meet where those 2 cubes meet. And so it turns out you get, instead of so this is 4, 3, 3, so this was cubes with 3 around each edge. If you reverse that, you get 3, 3, 4, which is tetrahedra. 3, 3 is a tetrahedron with 4 around each edge. And you can see that here, there's a tetrahedron out front, and there's 4 around the edge. 4, 3, 4, that was the Minecraft tiling, is self-dual, and you can see that from the symbol. Whoops, that should be 4, 3, 4. You can see that from the symbol because it's a palindrome. So if you swap the order, it doesn't matter. And here's the dual of 4, 3, 5. Now it's 5, 3, 4. So what is 5, 3? What is 5, 3 is it's a dodecahedron. 5 means it's made of pentagons. 3 pentagons meet in each point. That's a dodecahedron. And you can see it here, maybe. So here's a vertex of the cube, and then around it there is this dodecahedron. So before we go on to sort of, so the sort of theme of this talk is, OK, you got 3 numbers, P, Q, R. How high can you go? Right? I've shown you like 4, 3, 5, 3, 5, 4, things like this. What happens next? So I have to introduce something else before we get there, which is the concept of ideal vertices and ideal tiles. So in 2 dimensions, this thing only really happens when you sort of take the numbers to infinity. But in 3 dimensions, they show up much earlier. So here's a sequence of tilings by squares, 4, 6, so 6 around each square. And these are all hyperbolic, right? When I had that graph, these are all going way up here. So they're way above the curve that indicated the boundary between spherical and hyperbolic. 4, 6, 4, 10, 4, 20, you can keep going. And you can see that if you just sort of, what's happening here is that the angle of the square is getting smaller and smaller, and in the limit, it goes to 0. And you get a perfectly reasonable tiling of the Poincare disk model, where there are squares with infinitely many around each vertex. And so those have to actually be out at the boundary of hyperbolic space. They don't fit inside of space anymore. And the dual, so these have ideal vertices because the vertices are at infinity. They've got way too many squares around them. Down here we have the duals. Again, you just reverse the order. And so now what's happening is that the number of sides on each cell is going up and up and up. And so this is an ideal cell. This is an infinity gon. This is a tiling by infinity gons with 4 around each vertex. Hopefully everybody's happy with this because it gets worse. Okay, so 436. So we did 433. That was the hypercube. 434 is the Minecraft tiling. 435 we saw already. 436, now things get weird. So here's this cube, and again, I'll show you the sort of layers going outwards. So there's the central cube, 1 layer, 2 layers, and I've got space for an exocube here because there's supposed to be 6 that fit around here. What is the dual of this thing? 436, well, you know that what you're supposed to do is reverse the order to get 634. What is 63? 63 is supposed to be the cells that I make my tiling out of. 63 is a tiling of the Euclidean plane by hexagons. So this is what the dual cell looks like. It's not a finite polyhedron anymore. It's a Euclidean plane that looks kind of spherical, but it's a Euclidean plane. It's made out of hexagons. There are 6 around each vertex. 3 around each vertex. So we can go over to this simulation here and increase the edge degree from 5 to 6. And this is what it looks like. So there are these vertices that have, just as in the 2-dimensional case, they have infinitely many cubes meeting at them. Okay, great. So that's a little bit weird. They're going to get weirder still. We can start building the graph, right? So we have this 2-dimensional graph. Where are things spherical? Where are things Euclidean? Where are things hyperbolic? In 3 dimensions, there are 3 numbers, p, q, and r, and we can do the same thing. So this is p, the p-axis, the q-axis, and the r-axis. So this surface here, which I've labeled A, this is the boundary between spherical and hyperbolic geometry. And on that boundary, you get the Euclidean ones. So this here is 333. So what is the tiling, 3-dimensional tiling with 333? It's made out of tetrahedra, and there are 3 around each edge. That's the pentacoron. That's the, otherwise known as the hypertetrahedron, sure. And that's spherical. It fits on the sphere. The hypercube is in here. There's 6 of the uniform regular, the platonic 4-dimensional solids. And then let's see. Here's 434. That's the tiling. That's the Minecraft tiling. That's the only one that you get in this system. And then everything on this side is hyperbolic. So you don't get many spherical and you don't get many Euclidean. But I've drawn these other surfaces here. So what is this thing here? So this is the, let's see. This one here, p minus 2, q minus 2 equals 4. That's the same as the curve that I had for 2-dimensional tilings that separates the spherical from the hyperbolic 2-dimensional tilings. And so I've done that for the first 2 coordinates, and I've done it for the last 2 coordinates. Because something weird happens when you're on that surface, right? So that was what was happening here. I'm on that surface where the tiles that I'm using are not finite, right? They become, we get ideal cells. So it's one way around or the other, and I'm probably going to get it wrong. Let's see, PQ. So here, this surface here, B, that's a surface where you get ideal cells. And this surface here, C, that's the surface where you get ideal vertices. And so the question is, what happens on the other side over here, right? Can we make sense of plugging the numbers in where you've got more than ideal? Well, what happens, right? So we need to go from ideal to hyperideal vertices and hyperideal cells. So here's the Poincare-Diss model. We saw this is a square and this is an ideal square, and we saw tilings with those examples before, and you just keep going and the vertices just go outside of the Poincare-Diss model, and these 4 red arcs are supposed to make you think that it's a square. It's a little bit happier maybe to think about, if you're familiar with the Klein model instead of the Poincare-Diss model, you have straight lines for the geodesics rather than these arcs of circles. And so what is going on with this hyperideal square? Well, if you allow the vertices to be outside of the disk, then it just works. So fine. Why not? Let's see. Give me a second. There we go. OK, so here is a cube from the 437 tiling. So 4,3 means it's made out of cubes again, but I want 7 around each vertex. And in order to make that work, the vertices actually have to be outside of the hyperbolic space. Let me go over here and show you what it looks like from inside the space as well. If I go to 7, then the edges no longer meet. They just sort of end at the boundary of hyperbolic space. Well, and since I'm here, we can just keep going. 9, 12. So this is nice, but it's sort of hard to see what's going on, right? The edges just stop. There are no vertices anymore. So we wanted some other way to try and visualize this. So these are hyperideal vertices, and I'll do the same thing, just layer out a little bit. So maybe you can see around here that they're just cut off. The cubes are cut off at the corners, and you get these little triangles. And there's one triangle, and then so there are 5 triangles around here, and there's space for another 2 here, because you're supposed to have 7 around each edge. So that's what you need to have happen. So this is sort of what we came up with for how to try and draw a picture of these things. The inside of hyperbolic space is kind of boring in a way, because there's just these edges that go through that don't meet any other edges, but the boundary gets really interesting. So here what I've done is this is the cube, and I've colored the triangular end that gets cut off of this cube red here, and it induces sort of this cool pattern on the boundary of hyperbolic space. And so here's the tiling outwards gives this all kinds of crazy structure. And what I've done is I've taken this sphere and then I've stereographically projected that sphere onto the plane so we can see it nice flat. And this is the pattern on the boundary. So the red cube, you can see 4 of the corners. There's just maybe a little pixel of red there. There's another 3 corners there, and then there's 1 corner that's at infinity. And then you get all of this other extra structure. So there's the corners of the cube that sort of meet at one hyperideal vertex make a tiling of the hyperbolic disk, or an apparent tiling of the hyperbolic disk, where all of those vertices meet. But then, of course, there's infinitely many of these hyperideal vertices, and each one of them gets a tiling by triangles that looks like another copy of the hyperbolic plane. This is what the dual pattern looks like. So this has got a hyperideal, a hyperideal cell. So the dual of a thing that has hyperideal vertices has hyperideal cells. So this is a 7,3 cell. What is 7,3? So this tiling is 7,3,4. So that means I take 7,3 cells and I fit 4 of them around each edge. Well, what is a 7,3? That is a tiling of the hyperbolic plane by heptagons. So, well, fine. OK, we can do that. And then we can use them and stick 4 of them around each edge in 3 dimensions, and we get this tiling of space. And you get this extra feature where, so we call these things legs. So this cube has 8 legs that go outwards, whereas this cell has a head, I guess, is this bit that just sticks out onto the boundary that isn't associated with the vertex of the cell. OK, so, well, let's keep going. So 363, so that should mean something. So 3, 6, that's triangles 6 around each vertex. So that's a tiling of the Euclidean plane by triangles. But I'm going to put 3 of those around each edge. And this is self-dual because it's a palindrome. And so here are 2 dual cells. And you can sort of see maybe, so the blue cell here, it's got a vertex that's kind of at the limiting point of all of the legs of the white cell. And they're symmetrically related to each other. Here's the 373. So that's also self-dual, because if you reverse it, you get the same thing. Same thing, this white cell has this head up here, and there's a leg of the blue cell that goes into the same place as the head of the white cell. Of course, there are infinitely many other legs of the blue cell, and each of them gets a dual white cell as well. So then we just sort of said, OK, let's do everything. So we had that graph, that 3-dimensional graph, PQR, and you can say, well, let's just do everything in that cube. Well, at least let's do the the 6 boundary faces of that cube. So these are all of the honeycombs which are 3, cube, r. So, and we've tried to draw some picture of it. So up here, let's see, 3, 4, 5. Do I have this right? I think I do. So these are those. See if I can. I think actually maybe this whole corner down here. These are the spherical ones, and then we've got these sort of boundary pictures of the pattern that you get on the boundary of hyperbolic space for all of the hyperbolic ones, and you can go all the way out to infinity, and you get these, well, strange things going on. So this is another side of that cube, P3R. So again, we have that's the pentachoron, the hypertetrahedron, and there's a couple of other. This one here is our representative of the Minecraft tiling with cubes with infinitely many. Sorry, with 4 around each edge. So you get quite far into this. This is the last. Let's see, what is this? This is 636. So these are ideal vertices and ideal cells. So we can still sort of draw a picture on the inside of hyperbolic space, but then we have to go to these sort of boundary pictures where things are going through. Well, so you get a lot of variation. So this is one of the infinity sides of that cube. So infinity PQ. I mean, there's just lots of stuff here that maybe I shouldn't spend too much time talking about. PQ infinity. Notice this one here. It took us a long time to figure out what the picture of infinity, infinity, infinity looks like. That's what it looks like. These are the so we had those. I had those sort of slices, those surfaces that slice through the cube. So these are the ones with ideal vertices, and these are the ones with ideal cells. And so you can see various patterns here. It's nice here. You see these sort of regular Euclidean tilings popping up, and that's because of let's see. So these ones are R44. So you always see this square tiling coming from the 4-4. And here you see the hexagonal tiling, and here you see the triangular tiling. Okay, so we did some 3D prints. Having gone this far, let's try and make some pictures. Of course, we could only do the ones which had material vertices, the ones where the vertices are inside of space. Ideal are the ones where they're on the boundary. Hyperideal are the ones where they're outside of the boundary. So we have these 3D prints. I don't have them with me, unfortunately. But these are 2 dual ones, squares with 5 around each edge, and dodecahedra with 4 around each edge. This is a nice self-dual one, 353. This one's really nice. You never see sort of tilings with icosahedra because they're too big. But if you go to hyperbolic space, you can. So this one is a self-dual tiling by icosahedra, triangles, 5 around each vertex, 3 of those icosahedra around each edge. These are ideal in the dual, ideal vertices, ideal cells. And this is another interesting one. This is 444. So 4-4 means that you've got a tiling of the plane by squares, but then you somehow wrap 4 of those tilings around each edge to get a tiling of hyperbolic space. Another very pretty tiling. So we made some 2D sort of artworks based on this. So this is 464. So again, what is this thing? We've got squares with 6 around each vertex. So that's a tiling of hyperbolic space. And then we put 4 of those around each edge. And you can see all of these 4s here, and then the 6s, and you can sort of figure out why are they hexagons, why they're vertices with 4 around each edge. Where does the 4ness there come from this 4 or that 4? It's a little hard to figure out. You can move all of these things around and have different representations of hyperbolic space. 7-3 infinity, so that's heptagons with 3 around each vertex, but then you fit infinitely many of those things around each edge. This is another nice picture of 437, which has this self-similarity. So if you zoom in, these 4 things here are the same as those 4 things there. That's an isometry of hyperbolic space. And this was a sort of artistic interpretation of 373. So what is going on here? So I think we saw this before. This thing has hyperideal vertices and hyperideal cells. So what are we actually seeing? So the sort of cathedral catacombs here, we're inside of one of the cells. And this is its, we're outside of one of the cells. So this thing here is one cell. All the red things are also one cell each. They're actually isometric. It's just that one of them looks huge and the others look small. And then, so all we've done is drawn some of the cells, 5 of the cells, and none of the others, and drawn the boundary picture. And this is drawn in the upper half space model of H3. And there's a picture of infinity, infinity, infinity. Now, is the infinity here coming from this infinity, or that infinity? I have no idea. That's pretty much all I have to say. So if you go to hyperbolichoneycombs.org, then we have all of the images in high resolution. And I guess let me just finish with this thing. Let me just, this thing is fun to play around with as well. Maybe there will be a Bridges talk on this at some other point, but this is up on the web now. You can play around with it. I'll stop there. Thank you. Any questions before we go out for the photo? Yes?
Did you intentionally avoid 666? Was that?
Hadn't thought of that. If you go to hyperbolic honeycombs, I would be very surprised if it's not there, because we just generated lots of stuff. Future Henry here, we did generate the honeycomb of the beast, and it is on hyperbolichoneycombs.org. Yeah?
So I feel like I have a good idea of what it means for hyperideal or a sub-ideal polytope to be regular.
Right.
Can you say what it means for an ideal polytope to be regular?
For what?
What's for an ideal cell to be regular?
To be regular? Well, yeah, everything is regular. I mean, the Schneifeli symbols only describe things that are regular. Right. I mean, one way to think about it is like just define it by the construction. So the construction is, for all of these things, is you take a little tetrahedron with the angles chosen correctly so that when you reflect it around, you reflect around this edge, you get P, you reflect around this edge, you get Q, you reflect around this edge, you get R. And if you do that, then this is what you get. So it's got the same symmetries because that little tetrahedron is a flag of the symmetries. So that's a way to think about it. Question over there.
Have you attempted to make any sense out of non-integer PQ and R?
No. What would that mean? Oh, yeah. Right. Yeah, we haven't got to that. Maybe, yeah. Sure. Good idea. Question there.
Yeah. I liked some of your previous 3D printed work where you put a bright LED in the middle and
right.
It does it transforms in a very interesting way onto a flat surface. Have you tried that with some of these honeycombs?
Oh, sure. Well, I mean, if you have them out on the table and you've got a flashlight, it's impossible to stop people doing this. So, I mean, there isn't as clear a mathematical meaning from the sphere. But yeah, I mean, you get very pretty results, absolutely. Doug?
So in the pictures where you've got one of the 3 numbers is infinities,
yeah.
Like that bottom right picture,
yeah.
I'm struck by the resemblance of those images to the iterated Mobius transformations in Indra's pearls and David Mumford's.
Yeah, there's definitely connections. Yeah, so actually that's in the paper. We list a few. Here's some papers or images from papers that we found that look like our 734 or whatever. Yeah. I mean, it's all hyperbolic geometry, so there's lots of Mobius transformation things going on. It's the same sort of stuff. Yeah. If there's no other questions, question. Can you use negative numbers? You'll notice we didn't have any number lower than 3, in fact, because if you have a polygon with 2 sides, it doesn't have any area, so you can't really see it. Yeah, I'm not sure what a negative number would mean, but you should find out. Oh, one more question.
You said you had to figure out what the infinity looked like before drawing it. But I was picturing when you had this table, you have an algorithm and you just put in the Schlafly symbol.
To an extent, but there's so infinity. If there's an infinity, it changes things a little bit because you can't say, the angle of the tetrahedron is 0. So that's a little bit, and yet things are changing elsewhere. So there's a little bit of code to do there. It's also worth noting the way we drew these. There are choices in what you put in the center. So, let's see. There's a cube in the center. Great. Well, let's go to this one. Right. So here I've got a cube that's centered in the disk. This thing I cannot make centered because it touches the boundary. There's no sort of symmetrical way to put it in the middle. So you have to choose where you arrange things. Are you centered in the middle of a cell? Are you centered at a vertex of the cell? At an edge? There are choices you have to make in order. We did make some choices in generating these images. We tried to make as few as possible. Okay, I think it's photo time. Thanks everybody who came to the session.